This will be a quick summary, maybe about 15 minutes or so, a quick summary of what we did in Chapter 5 here throughout this unit. So we're dealing with logs and exponents primarily here, and we will begin with the exponents since that is where our chapter began. So in a nutshell, 5.1, we talked about growth and decay. Growth was simply when you multiply by a number greater than 1. So in other words, if you have 1.1, we can say that is a 10% growth. Okay? And that comes from 1 plus 0.10, okay? 1 plus the rate. All right, and that should look familiar to you. That pops up quite a bit throughout this unit, the 1 plus r and stuff like that. So if we're looking at decay, if I gave you 0.90 as my multiplier, then that says I had a 10% decay. Okay, or depreciation. Just like growth could have been appreciation. Right? Growth is the same thing as appreciation. Right? You appreciate making money. And decay is depreciation. Depreciation. Okay, so that was the main focus of Unit 1. In the first section, they also got into all the laws of the exponents. You know, the basic ones like b to the x times b to the y equals, that's right, b to the x plus y. B to the x divided by b to the y equals b to the x minus y. And of course, restrictions on here that b cannot be 0 and different things like that. You can look at that in more detail on page 170 if you'd like to. You also have the caveat b to the x equals b to the y. That implies that x equals y. Again, a lot of restrictions on b. In that case with 0, 1, and negative 1 being restrictions. Okay, b cannot equal 0 or plus or minus 1. So those were the same bases here. B, 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 B. Okay, and now we get into ones of the same exponents like a times b raised to the x. Well, you can distribute exponents through multiplication, not addition. A over b to the x, and likewise with division. Division and multiplication are the same. They are inverse operations. Multiplying by 2 is the same as dividing by 1/2, right? They're the same animal. So here we have the like bases. Of course, a to the x equals b to the x implies that a equals b then as well, with the same restrictions about a and b. They have to be positive. A and b are greater than 0, and of course x cannot equal 1. And then you have the power to a power b to the x to the y equals b to the x y. Alright, so those were the main focus of Unit 1. Keeping in mind, one thing I did not mention here, we'll throw it over to the side here, b to the negative 1 is 1 over b. Okay, we have that one, and by definition, b to the 0 is 1. There is Unit 1 in a nutshell. Let's keep on trucking along. We'll go to Unit 2, or Section 2, if you will, 5.2, and this is where they get to be pretty short. Talking about rational exponents here. So that was simply, let's write this down first, rational exponents. Okay, quick refresher on these guys. X to the 1/2 is the square root of x. X to the 1/3 is the cubed root of x. X to the 2/3 would be the cubed root of x squared. In general, x to the p over q is the qth root. How do you say that? The qth root, the root q, the qth root. Let's call it the qth root of x to the p. Okay, so that is your fractional exponents there. Trucking right along, we're looking at Section 3 now. In Section 3, we start talking about some functions. So 5.3, we're dealing with the exponential functions, and if you're given a couple points, exponential functions right here. Let's look at an example here where, let's say, you're given f of 2 equals 12, and let's say f of 0 equals 3. So remember, this is f of x equals y, and we know that y equals ab to the x, right? That is our general form of an exponential equation. So I'm going to take x and y right here. I could take x and y here if I wanted to, but 0 is always nice. So 3 equals ab to the 0. Remember, b to the 0 is 1. That means a equals 3. Now let's take our next x and y. 12 equals a, well, a is 3. B I don't know, but x I know is 2. Divide, I get 4 equals b squared. And I know you're not thinking to write just a 2 there, plus or minus. So our final answer, or in this case answers, is 3 times 2 to the x, or y equals 3 times negative 2 to the x. So that's our exponential functions there. This was where we first were introduced to a of t equals a sub 0 b to the t over k. Right, this was an example if something doubles every 3 days, right, it'd be to the t over 3, because every 6 days it would have doubled twice, so 6 divided by 3. Okay, k here was how long it takes to multiply a sub 0 by b. Think about what that means. If I tell you something has a doubling time of 5 days, and I want to know where it'll be in 15 days. So I have my starting amount, let's call it a sub 0. It's doubling every 5 days, so that's 2. And the time, I'm saying 15 days, it doubles every 5 days. So how long it takes to multiply a sub 0 by b? It takes 5 days to multiply a sub 0 by 2. Okay, so in this case, in a span of 15 days, it's going to multiply a sub 0 by 2 3 times. Right? This is really a sub 0 times 2 to the third power, which is a sub 0 times 2 times 2 times 2, or simply 8a times a sub 0. So it's 8 times the original, but it triples every 5 days, so we put a little 5 here just so we're not saying 15 days and raising it to the second 15 times, when we only need to do it 3 times because it doubles every 5 days. Okay, the other big piece of section 5.3 was the rule of 72. Okay, remember the rule of 72 says that the your interest rate, or percent, will equal 72 divided by your time, or your time will equal 72 divided by r percent. Okay, remember, this is the only time you don't write the percentage as a decimal. It says r percent, not just r. Okay, so if it's 10%, you're going to do 72 divided by 10. That gives you 7.2 years. And remember, the rule of 72 applies for doubling time. This is how long it takes to double. Doubling time. Double, double, double. Okay, it's like the Doublemint commercials. Double time. All right, 5.4 was where we got into the number e. Number e was defined, remember, as a limit. The first time you were introduced to that, of 1 plus 1 over n raised to the n, and that equals 2.71828, and there's much more to that, which is used and represented by the letter E. The letter E is what allowed us to do continuous modeling, continuous interest. In continuous interest, we deal with a lot of population, right? Bacteria growth, world population, different things involving population. So we use P oftentimes, so we'll put an arrow there. P equals your original amount, E raised to the RT. And remember, this is a decimal, 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 R, 10%, 0.1, 20%, 0.2, 15%, 0.15, decimal, decimal, decimal. We had our simple interest. So in other words, if things happen over the course of a year, simple interest, that's our boring old regular, our regular equation, a sub 0. The multiplier, 1 plus r raised to the t. Okay, that's y equals a b to the x. 1 plus r is our base, or our multiplier as we refer to it here often. Right, 10% increase, multiplier is 1.1. 10% decrease, multiplier is 0.9. Okay, so that's our generic equation. And then our compound interest, the real world stuff here. Things get compounded and you find quarterly values. You have businesses all report their quarterly finances. You have monthly interest statements from your bank. Okay, and that is A equals A sub 0 times 1 plus R divided by the number of compounds raised to the number of compounds times the number of years. Okay, so we're talking here. Is this quarterly? Well, if it is, number of compounds, 4. Monthly, 12. Daily, 365. Always? Wrong equation. Continuous model. Okay, so be careful. N has to be an actual number. Okay, and that of course is this N here, and the T, as it always has been, is time. Typically in years, not always, and of course the rate is as a decimal. Sorry, that's ugly, but that says decimal right here. Decimal. All right, so that's where we really got into our compound interest and stuff. And then we talked about logarithms. Logarithms in 5.5, I'm sorry, this was 5.4. Logarithms in 5.5 was our introduction. So our introduction to logarithms, we start with the definition. Okay, log base b of x equals something, let's call it a. That means, if that is true, that means b to the a equals x. Okay, and again, these are just letters. I could do log base z of t equals v, and that would simply imply z to the v equals t. Z to the v equals t. All right, so that is our logarithms. Remember the purpose of logarithms. Remember, they were not discovered, they were created as inverses of our exponential. So let's put a little more down here. Our exponential graph, we all know, crosses at 1, grows up there, nice growing bank account. And then if we draw in our y equals x line, the logarithm also crosses at 1, but on the x-axis. Looks like that, the reflection. Neither one of these get into the third quadrant at all, ever, never, ever, ever. All right, so there we go. The quick recap on the logarithms there. Okay, basically you got to do a lot of practice with these guys. Okay, a lot of practice on these, because once we try doing something, let's say for example log base 6 of 1 over 36, okay, if that equals -2, we need to know that 6 to the -2 equals 1 over 36. Well, that's 1 over 6 squared. And sure enough, that is a true statement. 1 over 36 is 1 over 36. All right, so there's logarithms. In 5.6, we start talking about the laws of logarithms. Laws, look out for the log police. Okay, you have log base b of m times n, just like in exponentials, multiplication becomes addition. Again, likewise, division amongst the logs becomes subtraction between logs. Okay, and then if you have a log base b, oops, that's a b, m to the p, remember that p can jump to the front and give you log base b of m. And then we have the typical, hopefully common sense one here. If all things equal, except for the letters here, that's going to imply then that m equals n, right? If log of something equals log of something, those somethings have to be the same things. All right, so there's our law of logs. Again, gotta practice, gotta practice, gotta practice. And the final piece here of our chapter was the changing the base formula. Okay, changing the base, change of base. And that one, that's kind of a fun one, you know, but it's real easy. Let's say log base b of c. That's simply log of c over log of b. And this base here can be anything you want it to be, as long as it's the same anything. Okay, they got to be the same. It could be log base 10. It could be natural log. Why would they be useful, you ask? Well, these are the guys on our calculator. All right, logs, we're going to have to use calculators often. Not always, often. Okay? So these are the ones we like the best because they're on our calculator. They're nice. Now, some of you guys got those fancy schmancy calculators, and you can put any base in there. And if you're interested in seeing that, I can show you how to do that. But that's not here nor there. The point of this was to give you a quick recap on Chapter 5, Logs and Exponentials. Hope you enjoyed it, and I hope you do well on your test. Have a nice day.